Let's discuss a question from K 2004. Okay, so what is given? A stainless steel tub, stainless steel tub of thermal conductivity 19 watt per meter Kelvin of 2 centimeter ID and 5 centimeter OD is insulated with 3 centimeter thick asbestos where the thermal conductivity is less 0.2 meters watt per meter Kelvin. If the temperature difference between the innermost and the outermost surfaces is 600 degrees Celsius, the heat transfer rate per unit length, so we have 0.94 watt per meter, 9.44 watt per meter, 944.72 watt per meter, D 944.7.21 watt per meter. So this is the problem. So what is given is, this is a problem on composite radial heat transfer through cylinder. So initial you have the ID and the OD. Let me draw it again. Then you have the asbestos. Okay, so hope I have drawn correctly. So this is 2, this dia is 2 centimeter and this is of 5 centimeter. So here you have steel and then on the top of that you have asbestos. Okay, and this is 3 centimeter thick, so the dia is 5 centimeter, the radius, so this is 3 centimeter thick. Okay, so what I will say is that you have the material here and here, so this can be always, it's better to draw a resistance network. Okay, so the resistance R1 of the steel and R1 of the asbestos. Now in the radial heat transfer, the resistance is given by ln R2 by R1 outer by inner 2 pi L K. So this is the resistance and they are in series, and heat flows, the heat transfer per unit length is asked, the temperature difference between the innermost and the outer. So let's say the inner is 600 degrees Celsius, the outer is 0, so that is all. So you have the total resistance is RS plus RA, the resistance of, because in series they add, so ln R2 by R1 2 pi, this is L which is perpendicular length to this paper per unit length, so that is per by Ks, plus ln R3 by R2 by 2 pi 1 into K asbestos. So let's first find out this. R2 initially will be 2.5 for the steel outer, and dia is, so R1 is 1, 2 pi, Ks is 19, and ln, as it is 3 centimeter, this is 2.5 plus 5 centimeter is the dia OD of thing, so 2.5 is the inner, so 2.5 plus 3 is 5.5 is the outer radius for the asbestos, and inner surface of the asbestos is at 2.5 because it's just mounted on the top of steel. So this is 0.2. So this is a straightforward problem. So let's calculate this first. So this value, actually if you calculate, comes out close to 0.635 both together, and the heat transfer rate is nothing but delta T by the total resistance. Delta T is 600, total resistance is 0.635, so this comes out to be 944.88 watt per meter. So the answer for this is 55 is 944 point, so the answer for this is 944.88, so close answer is C. So this is again a straightforward problem. Only thing is you need to just remember this, the resistance offered by radial heat transfer, what is the steady state radial heat transfer, thermal conductance. And once you, because these expressions are all derived for cylinder, for sphere, radial heat transfer through sphere, so you need to all remember this in order to solve this problems quickly. Let's discuss another problem from GATE 2004. So this is again a problem on lumped analysis. A spherical thermocouple junction of diameter 0.706 mm is to be used. Measurement of temperature of gas stream, the convective heat transfer on the bead surface, heat transfer coefficient on the bead surface is 400 watt per meter square Kelvin. Thermophysical properties, well, I will list it out. Thermal conductivity is K is 20 watt per meter Kelvin, specific heat is 400 joules per kg Kelvin, and density is 8500 kg per meter cube. The thermocouple is initially at 30 degrees Celsius, is placed in a hot stream of 300 degrees Celsius. The time taken by the bead to reach 298 degrees Celsius is, okay, so this is 2.35 seconds, 4.9 seconds, 14.7 seconds, 9.4 seconds. So this is the case. So you have a spherical thermocouple which is initially at 30 degrees Celsius initial temperature. Now it is placed in a hot stream where hot stream is measuring. Okay, the temperature of the hot stream is 300 degrees Celsius. So obviously after some time, if you just put the thermometer and take the reading, it will just show 30. It will take some time for it to build from 30 to 300, right? And once it stabilizes, that is the point you have to take the reading. Okay, so this is a classical case of lumped heat transfer analysis, where the bead surface, assuming that the entire bead behaves as a lump, as a lump, and the temperature rises uniformly. So we need to find the time taken by the bead to reach 298. So when its temperature will reach from 30, which is at the start, to 298 degrees Celsius, the surrounding is always 300. So this is a lumped analysis. So we can, so the important the formula is that, let's say at time t the temperature is T, so T minus the base temperature T infinity by T naught minus T infinity is e power minus HA by rho CV T. So this is again a pretty standard form problem. Okay, so T is the temperature at time T. Let's say that T, I want 298, ambient is 300, by initial it is 30, and the ambient is 300, e power minus, all this we need to substitute, H, heat transfer coefficient. Okay, now the heat transfer coefficient is given as 400. Okay, now A by V, A, because it's spherical, so A is the surface area, which is 4 pi r square, volume, it's a sphere, 4 by 3rd pi r cube, so this is 3 by r, and this is nothing but 6 by d. So d by 6 is V by A is d by 6. 400 into 1, because V by 6 I'll write d by 6, and rho is 8500, C is 400, V is diameter 0.706, 10 power minus 3 by 6, and time is something which I need to get it. Okay, so this value is what, 2 by 28, 2 by 30, and e power minus, okay, so I have to use a calculator for this value. So this comes out to be 0.39833 into t, and this is 1 by 15 e power minus 0.99833 t. So if I take ln 1 by 15 is minus 0.999833 t. So the time would be, so again let's use a calculator for this. So 1 by 15, if I use ln 1 by 15 and divided by what I got, so this value comes out closer to, so 2.7. I mean, if I just calculate, this comes out closer to 2.7 seconds. So the answer which is close is A, because so answer that is close to this is A, 2.7 seconds by the lumped analysis. So that's, there has been a mistake, guys. So this is 270, I think it went unnoticed. So this is minus 2 by minus 270, so this becomes 1 by 135, and when I calculate 1 by 135, this value comes out closer to 4.9 seconds. So we get an exact answer. The answer is B for this. Sorry about this case. So this is 2 by 270, which is 1 by 135. When you take ln and divide it, finally it gets 4.9 seconds. So all these problems, lumped analysis, the only basic formula is this, whether it's quenching or heating. Now here it was heating of the surface from starting from 30 to 298, and we have solved one more problem which was quenching in air or quenching in oil bath. So all these kind of problems of the formula is one and the same. You have to just properly use it. Let's discuss again another problem. Okay, 2004. This is another model problem. In a condenser, then a heat exchanger, water enters at 30 degrees Celsius and flows at the rate 1500 kg per hour. The condensing steam is at a temperature of 120 degrees Celsius, and the cooling water leaves the condenser at 80 degrees Celsius. The specific heat of water is 4.187, this is all we know, kilojoules per kg Kelvin. If the overall heat transfer coefficient is 2000 watt per meter square Kelvin, the heat transfer area is, okay, so 707 meter square, 7.70 meter square, 70.7 meter square, 141.4 meter square. Okay, so this is the thing. The water enters at 30, flows at the rate, the steam is at a temperature 120. Okay, so you have a condenser where the steam is at 120, and at the outlet it will be a 120. It just condenses during phase change. There is no change in temperature. Cooling water, it enters as 30 and leaves the condenser at 80. So this is how the cooling water goes. Cooling water temperature varies along the length. This is 30 and this is 80. So this is delta T1, which is 120 minus 30, 90. This is delta T2, which is 40. 180 minus 120 minus 80, 40. So we are going to use LMTD, where the heat transfer is given as UA delta T LM. That is nothing but LMTD. So delta T LM is delta T1 minus delta T2 by ln delta T1 by delta T2. So delta T1 is 90 minus 40 by ln 90 by 40. Okay, so this delta T LM is something which we need to know. So let's calculate this. So this comes out to be 61 0.67 is my delta TLM, so I can substitute here. But then I need to know heat transfer area. The overall heat transfer is given, but then how do I know Q? Now, Q can be written because I know the amount of heat, I know the inlet water temperature, inlet and outlet, so the amount of heat that is transferred is M specific heat of water, cooling water into change in temperature of the water. So it is 1500 is mass flow rate per hour, so let's do it per second. Specific heat is 4.187 kilojoules, so 10 power 3 10 power 3 per kg Kelvin. Delta T is 80 minus 30, so this is the heat transfer. So this you can get from each of the fluid, but the condensing fluid I don't know the latent heat, so the other way of getting is from the cooling water. I can just, because the internal energy, the heat supplied to the cooling water from 30 to 80 is the change in internal energy, which is MC delta T. Okay, so this is equal to your so this value, if I calculate, this value comes out to be 87.22 into 10 power 3 joules per second. So this value I have to equate it to here. So the 87.22 into 10 power 3 U, overall heat transfer coefficient is 2000. A is something which I need to know. Delta TLM is 61.65. So everything is known, only A I have to find out. So A from this comes out closer to 0.707 meter square after calculation. So this is one of the other model in heat exchanger, where basically an application of LMTD method, where first you will all the temperatures are known, get LMTD and then use this overall heat transfer coefficient equation for Q, and the other way of getting Q's is MCP delta T is for the hot or the cold fluid, but here the hot is condensing, so you can't use MCP delta T, you have to use ML, and that's the thing. So the answer for this is 0.707. Answer for this is option A. So let's do GATE 2003 problem. Okay, common data question. Heat is, so this seems to be an interesting problem. Heat is being transferred by convection from water at 48 degrees Celsius to a glass plate whose surface that is exposed to the water is at whose surfaces exposed to the water is at 40 degrees Celsius. Okay, the thermal conductivity of the water is 0.6 watt per meter Kelvin. Thermal conductivity of the glass is 1.2 watt per meter Kelvin. The spatial gradient of the temperature of water at the water glass interface. So at the water glass interface is dt by dy 1 into 10 power 4 Kelvin per. Okay, so you have the figure is given. This is the y-axis. You have water at 48 degrees Celsius is 40. So this is how the temperature varies, and more steep in the glass. So this is glass, this is water. Water far away is 48, glass is 40, glass surface. So there is a heat transfer like this. So the question is the value of temperature gradient in the glass at the water glass interface is -2 into 10 power 4 0.0 C 0.5 into 10 power 4 D 2 into 10 power 4. So this is one bit. The other bit is the heat transfer coefficient H in watt per meter square Kelvin is A is 0.0, B is 4.8, C is 6, D is 750. Okay, so now So here one thing what you have to understand is that let's do the problem number 1. You have water and you have glass. Okay, so as the conduction is taking, though there is a convection, but because of the glass surface, the immediate layer of the water will be in conduction. The immediate layer of water in contact with the glass will be just conducting, will be in a heat conduction mode only, so this happens anytime whenever you have a fluid passing over a solid surface or a stationary fluid. The immediate layer that is in contact with the solid is stationary, and the heat transfer media or the heat transfer mode is only through conduction. So one can write from on the water side, one can write kWA minus dt by dy is the heat transfer rate, the heat transfer through conduction in the water, right? And on the glass side, just at the interface, I can write on the glass side, I can write minus kGA dt by dy. So this is dt by dy for the water side, and this is so this is almost at the same point you're writing, but one thing on the water side and the one expression for the glass side, and both equating, because at the interface there is no loss. Whatever heat that is conducted from water to glass, so this is the heat, so both has to be same. So this is on the glass side, so both have to be same because there is no interface loss. So if I equate this, I get water is equal to kg dt by, now A is the cross section, you can say, I mean the cross section perpendicular area, which is same for water, which is same for both. So water, the spatial gradient for water is given is 1 into 10 power 4, and thermal conductivity is 0.6. Thermal conductivity glass is 1.2. I need to find dt by dy for the glass. So the dt by dy for the glass would be 0.6. So half of 1 into 10 power 4, that is 0.5 into 10 power 4. So the answer for this is C for the first bit. It's just simple thing, simple basic concept what happens at the solid liquid interface. So now let's look at the heat transfer. Let's look at the second bit. Second bit, one thing you should understand is that there's a water at 48 degrees Celsius, there's a 40. So the heat that is getting convected goes into the glass by conduction. So the convective heat in the water, that is HA delta T, T infinity minus the base temperature, is equal to Ka, heat is going, so Ka dt by dy. Okay, and I should write minus K dt by dy, but dt by dy, as you are, I mean we are not taking, we are just taking the magnitude only in the picture, so I am just writing Ka dt by dy. So this is for the glass and this is for the glass, right? What I am doing is the heat converted far away from 48 to 40, the heat that is converted goes into the glass as this. Okay, so from this I can write H, from this I can write heat transfer coefficient is what I need. From this I can write kg dt by dy. So let me write down in words, heat converted from water is equal to a heat getting conducted in the glass, So now we are not looking at the immediate layer, we are just looking at the far away. I mean just the total convected in terms of heat, we are writing in terms of convection on one side, and the other side is conduction through glass. So this is by T infinity minus dB. So these values if I put, so conductivity of glass is 1.2, dt by dy of glass is 0.5 into 10 power 4, which you already got on the first bit. T infinite is 48 and water is 40. So from this the value which I get is 0.075 into 10 power 4, so that becomes 7 750 watt per meter square Kelvin. So the answer for this is D. For the second part, it's 750 watt per meter square Kelvin. So these kind of problems, solid liquid interface, is the main focus in the convection problems. So this is what you have to understand. Okay. So let's discuss another question from 2007. So I'll not write down because this seems to be a bigger question. I'll just describe. So average heat transfer coefficient on a thin hot vertical plate suspended in still air. So you have a thin hot vertical plate, thin vertical plate suspended in still air. Okay. Assume that the plate temperature to be uniform at any instant of time and the radiation heat exchange with the surrounding is uniform. So the temperature any point as it loses heat is uniform. The entire temperature falls at the same pace and the temperature of this is uniform. The ambient temperature is 25 degrees Celsius and the plate has a total surface area of 0.1 meter square and the mass is 4 kg. The specific heat is 2.5 kilojoules per kg Kelvin. The convective heat transfer coefficient at the instant when the plate temperature is 225. Okay, the specific heat is given. I need to find the convective heat transfer coefficient at the instant when the plate temperature is 25 and the change in plate temperature with the time d by dt is minus 0.02 Kelvin per second. So at the instant when the plate temperature is 225, okay, at that point what is the convective heat transfer and the change in plate temperature with the surrounding is also given. Okay, so these kind of problems we need to, this is a lumped analysis where the entire plate. So this is a lumped analysis kind of problem where entire plate tends to lose the temperature at the same time. So this is like quenching in hot air. So we'll use our standard formula which says that minus HA by rho Cv to time T. Now what is given is that at an instant when the temperature is 225 of the plate, at that point of time, let's say the quenching starts. So this is 225 minus ambient is 25, base temperature. Okay, so let's okay, this is a standard, this is basic equation. So let me just simplify it because the rate of fall of the temperature is given. So is exponential minus HA by rho CVT. So if I differentiate this dt by dt, I'll get T naught minus T infinity and exponential is minus HA by rho CV and d is same thing, minus HA by rho CVT. So at the point when, at the instant when I start T0, at the instant when temperature is 225, at that time this is 0.02 and T0 is 225 minus the base is 25. Okay, and minus HA rho CV is what I am going to write, but I am starting at this point, so exponential T is 0, so e power minus 0 is 1. So this is 0.02, this is 200 minus H is what I need, surface area is 0.1. okay, and well, what I don't know is my density. So density into volume is mass, which is given as 4 kg, and specific heat is given as 2.5, 10 kilojoules, so 10 power 3. So this is a straightforward problem on the lumped analysis. Only thing is you have to understand that it behaves as lumped analysis. So then, okay, so this answer for this comes out to be 10 watt per meter square Kelvin, that is the unit. So it's a straightforward problem, lumped analysis problem. Only thing is the rate of change in the temperature at the instant when it's 225. So from that point of time, so assume that the plate is at 225. At this moment I want H. So this is T naught and rate is dt by dt. So first, instead of directly using the formula, I just differentiated, I just written like this and then differentiated, and then I wanted to substitute it to get the H. So it's 10 watt per meter square Kelvin. So answer is T. This is again another standard kind of problem which you will find in lump. So I think we have done a similar problem for this where directly the rate of fall was asked, but here the rate of fall is not asked, but you are you are given with a thin vertical plate. So first you will feel it's a convection problem, but no, the statement that the entire temperature falls uniformly, that is important, or that is a sufficient indicator that it's a lumped analysis kind of problem. Thank you.